Hello, and thank you for giving me the opportunity to present the eOTS solution provided by ETAP. My name is Derek Dean, and I am the Department Manager of the SCADA and ADMS departments in ETAP, and am heavily involved in the design, development, and testing of the eOTS product. During this presentation, I will discuss some of the key features related to the eOTS product. During this presentation, I plan to provide an overview of the eOTS solution, the pains and challenges facing various industries, a highlight of the ETAP solution, the value which the ETAP solution provides, the technical capabilities where I will provide an in-depth demonstration of the software in action, some case studies where the eOTS has been implemented, and finally a brief summary highlighting the key points and takeaways. It is important to have a clear definition of what we mean when we say Electrical Operator Training Simulator. An eOTS is a computer-based training environment which allows operators to perform common actions and observe realistic responses to those actions as relating to an electrical network. Note that I've highlighted the realistic responses because this is a key feature that can be very difficult to achieve in the industry. Leveraging the vast knowledge of electrical systems and analytical engines, the Operator Training Simulator provides a full-featured model-based operator training simulator. So this is a digital twin. This is also a software-in-the-loop simulator. The solution integrates with ETAP SCADA and advanced applications. It utilizes ETAP analysis engines for a complete training solution for all aspects of the electrical system. And there is an integrated trainee evaluation platform for the trainer. Operator error can be due to personnel turnover, lack of knowledge and familiarity with every aspect of the network. Complexity of systems can make it difficult to predict how the system will behave. For instance, there's a lot of scenarios where unexpected results can happen because of the dynamics of the system. Additionally, there's a lack of training, certification programs, and metrics to evaluate the operators. Operator errors result in delayed, inefficient, and incorrect actions. For instance, it is common that an operator can find a way to achieve the goal, but it isn't done correctly. Precious time can be lost as a result, and this can lead to loss of productivity, outages, fines, and even injury or death. Every electrical system has its own unique challenges which can benefit from an operator training simulator. This slide shows just a small subset of some of the common requirements for an OTS where the industry has failed to adequately simulate. This includes simulation of plant startup and shutdown, consideration of electrical system dynamics and steady-state behaviors, model plant behavior qualitatively, and to use simulated or actual operating data to replicate the plant operations. There is a major lack of model-based electrical operator training simulators in the industry today. Current eOTS solutions support minimal simulation. Without a model-based solution, the continuity coloring, meter readings, etc., either require significant manual work to calculate the behaviors, or more likely, this intelligence is non-existent. For instance, only the symbology is changed often, and this simulator doesn't take into account the nuances of the system. For instance, how the flows behave with energization coloring, adjustments in loading. It doesn't take into account transients in the network with inrush currents, motor starting, etc. Don't take into account automatic protective equipment like relays. Overall, conventional eOTS solutions lack intelligence and don't accurately reflect how the system behaves to the various actions by the operators. In some circumstances, dedicated hardware simulators are implemented. In these cases, the hardware is extremely expensive, and integration is very time-consuming and also costly. Additionally, the maintenance and system updates are very difficult and costly for these systems. For instance, if a new substation is added, all of the mapping must be done on both the hardware simulator and the SCADA side and modeled. so this is a very costly endeavor. Actual hardware in the loop for simulation is also done, where relays, PLCs, DCS, and controllers are actually purchased and connected to the SCADA system. This has become cost prohibitive as there are other options out there and rarely seen in the industry. This slide shows just some of the industries which the ETAP eOTS solution can be very beneficial. The ETAP eOTS is a solution for all industries because ETAP knows power for all industries. Some key features that the ETAP eOTS solution provides is a realistic response to actions taken by operators, evaluate normal and emergency conditions, and we've gone to great lengths to support mimicking the existing PMS, SCADA, and OMS operation screens, even if it's a third-party SCADA that we need to mimic. One major feature that is unique to the ETAP eOTS solution is the system dynamic support. This is because the transient stability engine is utilized within the OTS simulator. This gives the trainees a very realistic window into how the system actually behaves. For instance, when a large transformer is energized, the associated inrush can be seen in the operator screens. This is something that you can't really see in other non-model-based OTS solutions. Another key feature is the fact that the relay protection modeled within ETAP is taken into account by the simulator. For instance, if an overcurrent relay is modeled in the ETAP model, it will automatically trip the breaker if the required current is detected. This is rarely seen in the conventional OTS, and if the behavior is seen, it requires a significant amount of effort to program in, while in the ETAP solution, it just works out of the box. So as long as you have the system correctly modeled, you're ready to go. This capability combined with a dynamic response allows for significant insight for the trainee for how the system behaves. ETAP and third-party controllers can already be modeled within the ETAP software. For more information on this, I recommend that you watch the Microgrid controller webinar. The ETAP eOTS also takes into account this behavior by the controllers. Controllers can include, however, are not limited to local and or centralized GMS, microgrid controllers for DERMS or any other purpose, and load shedding controllers, and many other types of controllers can be modeled. Here's a quick architecture showing the flow of information in the eOTS. In the center sits the instructor, which can receive real-time data from the existing SCADA, historical data from the ETAP playback service, or simulated data from the ETAP analysis. From here, the trainer can use this real-time, historical, or simulated data to initialize the trainee's environment. The trainee then can run through the training plan, performing operator actions and seeing the system response provided by the digital twin, all while operating on the various SCADA interfaces. Finally, the trainee actions are sent to the trainer for review. Some of the actions a trainee can perform include protective equipment open and close, transformer tap position changes, GMS mode and regulating set points adjustments, generator mode and set points, operator notes and service tags, alarm management, load shedding management. Additionally, trainers can start a training scenario. All operator actions can be performed by the trainer. Injection of trip signals, increase and decrease loading, renewable increase and decrease, islanding and interconnection conditions. Note that this is just a subset of the actions that a trainee or trainer can perform in an ETAP OTS solution. As mentioned previously, the entire suite of ETAP real-time products are supported within the ETAP eOTS solution. The only difference is that rather than receiving data and sending controls to the field, this information is available from the eOTS simulation engine. The ETAP eOTS solution provides for both an individual and team assessment option. So each individual trainee can train on their own environment and work in a bubble, or all trainees can point to one simulator and the team can be evaluated together. The ETAP OTS solution archives alarms and events, snapshots of real-time data so that data can be reviewed step by step, trends and reports, and all operator actions. Essentially all information that is necessary for the trainer to evaluate the trainee is archived and available for review later on. Evaluation of operator awareness and readiness is critical for any operation. To facilitate this, the ETAP OTS solution prepares trainees to respond to malfunctions and emergencies through injections of events, messages, and disturbances. It allows trainees to evaluate contingency responses to both steady state and dynamic scenarios using actual system operating interfaces with realistic learning simulations and logic schemes. It effectively certifies and confirms operator readiness as the trainer creates pre-configured scenarios to simulate realistic situations while allowing operators to respond to these disturbances. And it supports certification and recertification as the electrical network grows and changes through time. Here are a few points where the ETAP OTS solution can provide immediate value to your operations. Reliable. The eOTS high-fidelity model uses the ETAP digital twin platform to provide a dynamic simulation for system-wide plant operations. Competence. Improve operator competency, confidence, and knowledge for better plant operation. Flexible. Virtual training using the ETAP platform allows for reproducing realistic plant behaviors with identical power system operational environments. Configurable. Easily and quickly configure the OTS settings and scenarios to replicate various operation conditions. Affordable. No hardware dependency means using ETAP software in the loop will provide fast and affordable deployment of the OTS solution. Maintainable. You can utilize the eOTS over the plant lifecycle, from the design to operation phases to improve productivity and efficiency. The ETAP OTS solution allows companies to avoid unplanned outages caused by human error. This reduces risks associated with operator missteps with a real-time operation simulator using an ETAP digital twin model. The eOTS challenges operators to learn about and gain knowledge of the behavior of the power system and associated processes before facing real-world situations. It helps to avoid mistakes by wrong switching actions by supporting approved switching sequences of operations to guide operators where operators can follow tested and approved switching orders for various contingencies, normal operations, as well as emergency and abnormal conditions through virtual simulation. Trainers and trainees can use predictive simulation to avoid wrong switching actions, allowing individuals to identify how the system will respond to the operator actions in simulation mode before implementation, which is a great learning tool and assistance during actual operations. This supports safer operation while improving performance and productivity using the high-fidelity digital twin with dynamic simulation. ETAP OTS reflects the realistic operations and control responses of the actual plant. It ties together transient stability simulation with emulated automatic controls, including relay characteristics, interlocks, exciter, AVR, and speed governor generator capability, etc. The high-fidelity digital twin provides trainees the ability to learn how to react correctly when a similar situation occurs in the actual plant, resulting in fewer equipment stresses and the ability to correct procedure errors. Simulation of controller actions, such as load shedding, allows for training with the realistic response as well as validating load shedding logic to prevent costly interruptions. Too much load shedding can cause loss of critical processes. Not enough load shedding can cause total loss of production, unsafe operating conditions, and environmental concerns. Validation of the load shedding can prevent costly outages and equipment damage. Some very beneficial byproducts of the ETAP eOTS solution is that it allows for the user to improve model accuracy and reduce validation time, debug the electrical system, identify potential hidden problems, predict and resolve the cause of operation problems, validate solutions and learn from past experiences, make operation decisions with confidence, and ensures accuracy, predictability throughout the facility lifecycle. The value proposition that ETAP provides is that it is a solution that with a complete and accurate representation of the electrical system, no costly hardware simulators required, little effort to maintain and update the system, built-in evaluation tools for certification, support for all industries. Next, I'd like to demonstrate a few key capabilities of the ETAP OTS solution. First, I will demonstrate the initialization of a training session for one or more trainees by the trainer. With the ETAP OTS solution, it is possible to initialize a training session with the current real-time loading in the system. As you can see here, I have the actual real-time measured data in the field. The playback data, so here I can go to a historical snapshot and use that loading for my initialization. Here you can see that I can navigate through snapshots in time. Or I can use my simulated data. So in this case, I'm going to use simulated data by creating a study case here called LF_scenario6 and configure my loading for this scenario at 100%. Next, I set up the config. In this scenario, I want to show to the trainee that he must have both transformers online in order to start the large motor. So I'm going to open up this breaker to ensure that the initial conditions will not be successful. Next, I run my study and confirm that this is the initial condition that I'm happy with. With that study, I start the scenario wizard and create a new scenario. In this case, I'm going to call it training scenario 6. And this is where I set the various critical information about my study. So here I'm going to set my study case to that load flow scenario 6, set my config to the motor starting config. Here's where it's critical. When you check the archive for OTS checkbox, this archives this study to the OTS environment. You can use real-time data, archive data, or in this case, just use my study case data, which is just the data, the loading and config from the study case. When I run my scenario, it creates a file for my initialization. So if I navigate to my initialized training session, now I have that training scenario 6 defined here. This is in the initialization console. Now I can set some details for use later on. I can give it a more user-friendly name, provide some information about what this scenario tests. So in this case, it's 100% loading, and I want to test my motor initially offline, and then I want to test starting it with a single transformer. Now I'm going to send this scenario to only trainee 1 at this point. This is done by clicking the send button. See that there is a confirmation indicating that trainee 1 has received this file for initialization. This user interface allows you to also visualize other scenarios that have been created in the past. Here we can see scenario number 5. So to recap, in this demonstration, I've, as a trainer, created a new scenario that I injected into trainee number 1 to be able to use for a training session. Now that I have demonstrated the initialization of a scenario for the trainee from the instructor's perspective, I will now demonstrate the initialization process for the trainee and then run through a few scenarios. To start a new session, the trainee must first select Start Training Simulation. This will bring the console online in simulation mode with the loading and configuration as defined by the instructor in the previous step. Note that at any time, the trainee can restart the training simulation to start over from scratch. This means that the trainee can independently self-train a given scenario as many times as they would like. See how the telemeter data is updating as if it were real-time data in the field. In this case, I'm going to close CB18 to attempt to start the large motor called MTR1. See how the standard controller interface is launched when you double-click it, and you can control it just as if it's a normal tag. In this case, we have an unexpected result. Instead of the motor energizing, we see a large portion of the network is de-energized, and there is an error indicating that the command was unsuccessful. Note that this is due to the overcurrent relay here. Looking at the alarms, we can observe an overcurrent trip alarm associated with circuit breaker 2A-1, a CB open alarm associated with circuit breaker 2A-1, and a failed control command for CB18, the CB that we attempted to close. This indicates to the trainee that starting this large load under these conditions will result in relay protection, and so the operator must make changes to the network before he can perform this action again. At this point, the trainee can reinitialize the environment, or in my case, I am just going to simply close the circuit breaker 2A-1 to restore to the previous state. Next, the trainee should know to either decrease some load or to bring the second transformer online so that the inrush from the motor starting is not too significant. Here we can see that I've closed that circuit breaker and we're ready to rerun the test. When we send a close command to CB18 now, the CB stays closed. We'll see here. And the motor starts up without de-energizing any other portions of the network. Another critical thing to note in this example is the trend showing the real and reactive power associated with the large motor. Using the standard SCADA trending tool, we can see that the load starts at 0, quickly jumps up to 12 megavars, then after a few seconds slowly settles to its steady state operating condition of roughly 2 megavars. Note that a typical OTS that doesn't take into account the dynamics of the system would never model this behavior, and the insight the operator gained about the relay protection would never have been learned. Next, I will demonstrate how load shedding schemes can be taken into account by the training simulator. In this example, the trainee has been instructed to isolate the network from the utility grid. The first step is to start up the training simulator scenario as demonstrated previously. Note that in this example, I did not show the steps of the trainer creating the scenario for the demonstration, just to save time. Now that the scenario has started, we can see a few things. First, genset C is offline. We can see that it's grayed out and the circuit breaker associated with genset C is open. We can also see how much generation the utility interconnect is providing. When I show the ETAP load shedding monitor, we can see that in the event of a utility trip, 5 loads shall be tripped in order to compensate for the loss of power supplied by the utility. At this point, the operator should know that we should not isolate from the utility without making corrective actions before. However, if the trainee decides to open the utility interconnect regardless, as I'm doing here, you can see that a number of the loads on the right screen become de-energized as a result, as well as utility being open as well. Additionally, when we look at the alarm screen, we can see that there are a number of alarms generated for each of the loads, the utility circuit breaker, as well as an alarm for the load shedding command in the first place. So here the trainee can understand that some actions that are performed can cause additional trips based on the load shedding scheme. This is something that is not possible under a standard OTS solution because the controllers and load shedding solutions are not taken into account with the OTS. Next, I will demonstrate the evaluation process from the trainer's perspective. Once a trainee has completed a given scenario, or all of their scenarios, the trainer can review them in a step-by-step manner, reviewing each action and the results of these actions. A trainer starts by selecting View Trainee Playback. Here the trainer can select which trainee's environment to connect to for review. Once the trainee is selected, the recorded snapshots are available here. Note that any alarms that are generated are indicated by the left panel. So now I will select a snapshot and display the results on the HMI. The trainer can use the built-in playback tools to review the step-by-step actions performed. See how the trainer can see the initial state where the motor is offline, and as we step forward in time, a large portion of the network becomes de-energized. This indicates to the trainer that the trainee performed an incorrect action. As we continue to step forward in time, we can see that the trainee learned from the previous steps and now is able to successfully start the motor. This is, of course, after closing the other circuit breaker, which allowed the power to be shared. When the trainer launches any applications while in trainer mode, these applications automatically connect to the trainee's environment. For instance, here I'm launching the event viewer and seeing all of the operator actions, alarms, events, etc. Here we can see the load shedding actions performed previously. Finally, I am demonstrating the trainer connecting to the trainee's trend lines. In addition to showing historical trends, the trainer can see the live update trend in real time to see exactly what the trainee is seeing right now. In this case, I am interested in the motor startup that was done earlier on in the demonstration. As is the case for all of the other applications in the training environment, all standard SCADA features are available for the trainer and trainee. Here I can zoom in and zoom out, export the results for a final report, and do all the other capabilities that we can do with an ETAP real-time implementation. Since most trainees prefer to train in an environment that closely matches their existing SCADA, the primary SCADA application has been significantly enhanced to allow administrators to closely match any existing SCADA solutions so operators can have a common look and feel when training on the ETAP OTS. Although SCADA screens can be automatically built using the ETAP model as a base, these screens can be significantly modified to match your existing SCADA. Enhancements including user-defined custom symbology, many enhancements with coloring and alarming, headers and footers development, and many more. For my first example using the SCADA screens, I will just demonstrate a trainee operating the tap position using the SCADA view. I will start by navigating to the correct HMI using the top navigation, then select the transformer dialog and navigate to the tap position page. Here, I will increase the tap position a number of times. Note that for this scenario, I am adjusting the primary tap position, so this should have the effect of decreasing the overall voltage on the secondary side. So here are my raise commands. If you notice on the left side, the bus voltage is actually decreasing as a result of this. Next, when I load the trend page, you can see the dynamic response of the tap changes here. Note that these tap changes affect the entire network and how the entire system behaves as a result of changing these tap positions. Next, I will demonstrate how the training simulator can model a third-party GMS controller and successfully simulate the behavior of a dynamic system with a custom controller. The SCADA HMI was created by the engineer to closely match an existing HMI. Note that no additional development was required by ETAP to create this HMI. Here, a user can set the GMS mode, set the regulating set points for the active power and the power factor. Here we can see all the generators, what island that they're currently in, as well as what the controlling source is, either the operator or the GMS. Additionally, we show the real reactive power, the priority, what machine is isochronous. All of this data is available to the HMI. Right now, LG7 is the isochronous machine as indicated by the green, and the fact that it is priority 1. Here I will demonstrate sending a manual raise command for the frequency. When I press this button, you'll see that slowly the real power increases for the generator. Note that we take into account the actual generator behavior, so the raise is actually quite slow, when in other simulators it might happen very quickly. So here we can see that the real power has moved from 14.01 to 14.1, or a little bit higher than that. So then multiple raise commands can be sent to achieve the desired real power for this generator. From the trainee's environment, I am now navigating to the OLV for LG6 because I would like to take LG6 offline. See that when I attempt to trip the generator, I get an error message indicating that the CB can't be open while the generator is running. This is because there is loading on the generator and this interlock has been configured for this system. Additionally, you can see that an alarm has been generated on the top. Next, I will launch the same view in trainer mode. We know that it is in trainer mode because of the indication on the upper left-hand corner, as well as the blue header coloring. When I attempt to open the controller dialog as a trainer, you should see a lot more options. Here's where the trainer has the option to inject one of the many different actions. In this case, the trainer is going to send an overcurrent trip signal to the trainee. Note that an action can be sent to multiple trainees at the same time. In this case, I'm just sending it to the one. Here I've sent the command, and now we can see that on the HMI, the circuit breaker has opened. Additionally, we can see that the generator is offline and that all the flows show 0 for that generator. And now note that the previous generation associated with LG6 has now been picked up by the isochronous machine, LG7. So you can see the red line going to 0 for LG6, and then the green line going up significantly for LG7. Now, as time goes on, you can see that all of the other generators are having commands sent to increase real power in order to bring that LG7 generator, the green line, back down to its regulating set point. Note that this doesn't happen instantaneously because it takes into account the dynamics involved with the generator. While that generation is decreasing, the trainee can now have good insight as to how the system should behave in this scenario. This segment demonstrates the following critical capabilities. 1. The creation of custom HMIs from their existing SCADA systems to provide operators the exact look and feel they expect in the actual environment. How interlocks can be configured into the system. These interlocks can prevent operators from opening or closing CBs until certain criteria are met, like generator loading, adjacent CB is open or closed, and many other conditions. How the trainer can override these interlocks on an ad hoc basis. How the trainer can inject trip signals and other ad hoc commands. In this case, an overcurrent trip was injected into the system, which resulted in a CB trip and generator to go offline. And lastly, how third-party controls can be configured in the OTS environment to provide the trainee a realistic understanding as to how the system actually behaves dynamically, giving the operator a crucial insight into the real-world environment. Here I am going to skip forward and review the entire event in the trend as an operator would. See how the isochronous generator has finally reached its regulating set point after about 3 minutes, and all of the machines have reached their new static operating conditions. Under a standard OTS, first, it is very unlikely that an event like this can be simulated, and even if this is possible, it is likely that the generators will immediately reach the new static operating condition rather than slowly reaching these values, which is the behavior in the field. Here I am showing how a trainer can inject complex actions with a click of a button. With a single click, I can trip multiple fuses which connect one subsystem to another. Now we can see in the GMS page how there are two islands called J1L1 and J2PD. With this, the GMS has promoted another generator to isochronous mode, so each island has its own isoc machine. Again, we can see this event in the trend view. In summary, the ETAP eOTS solution is a complete software-in-the-loop OTS solution for any electrical system. It simulates actual events with a realistic system response, giving the operators the tool to understand how their system will respond. It benefits from the decades of knowledge ETAP has proven over the years to provide a comprehensive training simulator, coupled with the enhanced SCADA tools for trainees to learn using the same look and feel as currently used in the field. With a model-based approach, this solution provides for a flexible and maintainable platform to build on for the future. This includes built-in tools for self-learning for remote and in-class training, including real-time feedback and trainer evaluation tools for certification.